So now we're going to talk about coefficient of variation. And coefficient of variation is one of these really important summary statistics that is a measure of dispersion. And at its simplest level, coefficient of variation is the standard deviation of a random variable divided by its mean. And coefficient of variation is often used to compare different items, like two different demands for two different kinds of products. And we can compare their coefficients of variation to see how similar or different their characteristics are. We've seen before that if we have a monthly random variable that is the sum of 20 daily random variables, right? So if we have monthly random variable m and 20 daily random variables di, and we assume that the di's are random are independent and identically distributed as d, that's normal mean mu d sigma d, and if m is normally distributed with mean mu m and standard deviation sigma m, then we have a mapping between these two time scales of that mu m equals 20 mu d and sigma m equals square root 20 sigma d. And then working the other way, we see then that mu d is mu m divided by 20, and sigma d is sigma m divided by the square root of 20, right? And so we have this mapping back and forth between them. And so we now want to look at sort of this characterization of random variables in the context of the coefficient of variability. And so if we look at the CV, or the coefficient of variation, then maybe we should first quick point out that it's coefficient of variation, but sometimes it gets said incorrectly as coefficient of variability, as I just did, but that happens. So if we think about, okay, how do we define this in terms of the monthly and the daily random variables, we see something quite interesting. So let's just take as an example that we have a random variable as an example here. Let's take m, and say it's normally distributed with mean 20 and standard deviation 10. And then the daily random variable that's equivalent to that is normally distributed with a mean of 20 divided by 20 and a standard deviation of 10 divided by square root of 20, or it's normally distributed with mean 1 and standard deviation 2.24. Right? Now we want to look and say, let's look at the coefficient of variation for both the monthly random variable and the daily random variable. And to do that, we just take the CV of m, and that just equals the standard deviation 10 divided by the mean 20, or a half. Right? And if we do the same thing for the daily random variable, its CV day is 2.24 divided by 1, or 2.24. And what we see now is that this random variable for the daily demand is different than the CV for the monthly demand. And why is that? I think at first this might be somewhat surprising, because these are both looking at demand, and they're actually looking at something that is sort of a transformation of the other random variable, right? One is the aggregation of the other the daily is the disaggregation of the monthly. But what we see here is we've got two different time scales. And so if we look at demand at a daily level, there's a lot more volatility than there is at a monthly level. we have a word to describe this, right? This is pooling, where the monthly random variable is pooling over time, right? And by pooling over time, the monthly random variable is more stable, right? The high days balance out the low days when we're summing over 20 of them. But if we have to plan for just one day, there's a lot more volatility in that day. And so one of the questions we have to ask when we're looking at coefficient of variation is, what is its underlying time scale? And this helps us demonstrate that. Now, something else we have to think about is the stability measure of a random variable. Very often you'll hear this sort of rule of thumb, which is that a stable product has a coefficient of variation of less than half, and that's stable. And long ago, when I was a doctoral student, I looked this up to try to see, where does this actually come from? Because I would hear this rule of thumb, CV less than a half is stable. And I'm like, well, what does that actually mean? And it turns out the earliest reference I could find to it is in a book by Robert Goodall Brown, Decision Rules for Inventory Management, which came out in the 60s, I think, maybe the late 50s. But it's just stated as a fact. Couldn't find it anywhere. So the best intuition I can have that explains this is as follows. If your CV is less than a half, then that's the same as saying that sigma divided by mu is less than a half, which, just algebraically, is that 2 sigma is less than the mean. Well, if we think about what 2 sigma is, right? 2 sigma is roughly, 98 percentile protection, sort of at the 2 sigma level. If we've got this normal distribution, mean and sigma, we're at about the 98. If we think here that this is the mean, this mean plus 2 sigma, this amount here is 98% of the probability under the curve is going to be to the left of this mean plus 2 sigma. So if we were holding inventory to protect 2 sigma, what that would be is less than a month's worth of supply, because it's less than the mean, but it would still provide a very significant level of service. It's sort of, I think, relatively unlikely people are going to stock a higher level of service than that. And yet, by so doing, we're still only committing a month of supply. And so I can see how that's a definition of stability. But it's very important to realize the underlying time unit here. So when we're looking at this claim couldn't possibly be made about daily random variables. This is really a comment about a monthly random variable.